Welcome back, everyone. In this video, I will be finishing up the limits at infinity section. Where we left off was at number 6. We want to do the limit as x goes to negative infinity of x cubed minus 3x squared. And what you can think about when we're doing this is not going to be similar to number 4 up here because of the radical issue. But we are going to have an issue if we try to evaluate it. In general, when you do a limit for a polynomial, it's always going to give you infinity or negative infinity. Unless if it's just a number. I should say if it's just a number, like the limit as x goes to negative infinity of 3, then it's just 3. But a polynomial, as long as its degree is greater than or equal to 1, which means it's not just a number, always has limit as x goes to infinity or negative infinity, doesn't matter, as plus or minus infinity. Now, sometimes the way polynomials are written, you can plug it in and you'll actually get infinity plus infinity or negative infinity minus infinity, which is not indeterminate because infinity plus infinity would be infinity and negative infinity minus infinity. This is just subtracting two really big numbers, which makes it negative infinity still. But sometimes you'll get infinity minus infinity, and that's our indeterminate. And just for the sake of this problem, I'm not going to plug it in because it might be one of the two that work, and I want to show you how to do it otherwise. Now, how are we going to evaluate this limit? Well, for starters, one thing I want to mention is in terms of infinity or negative infinity, if we don't really care, if we just want d and e, then this is just d and e because it's a polynomial. But how are we going to do this? The strategy is kind of similar to what we've already done, but definitely different as far as you need to start it correctly. All right, so one way to do it would be, you don't really have a fraction, but if you divide everything by the biggest power of x, then you could also multiply by that same power. But what this would amount to is actually factoring out the largest power of x, and that's what we're going to do. But this is very different from your normal factoring. Usually when we factor something like this, we would want to factor out the smallest power of x, but we want to factor out the largest power of x. Okay, so when we do that, this doesn't matter if it's the limit's going to infinity or negative infinity. We factor out the largest power of x, which is x cubed. Now, when we do that for the x cubed, that becomes 1 minus 3. Well, what happens when we factor out x cubed from x squared? We factored out one more x than it really has, which means we have an x in the denominator. And if you want to verify this, distribute that back in, make sure you can see that it is x minus 3x squared. All right, but why is this helpful? This is helpful because while we don't have a limit rule for something like this in general, we do have our limit rules, our new ones from above, if we have x to a power, just a number, or something over x. Okay, and when you multiply, it makes it a lot easier because a property of limits that we're going to use here is we can find the limit as x goes to negative infinity of x cubed and then multiply by the limit as x goes to negative infinity of the thing we're multiplying by, 1 minus 3 over x. Okay. We really haven't used that in this section, but when it comes to polynomials, you do use that. Now, when we go towards negative infinity of x cubed, this, because it's negative and the power's odd, this is actually our negative infinity one. Now, when we go towards negative infinity of this, 1 is just a number, so it's 1 minus something over x is 0. It doesn't matter if we go towards positive or negative infinity, so this is just 1 minus 0, which is 1, and negative infinity times 1 is negative infinity. And that's all there is to it. Now, there are a lot of ways you can memorize sort of based on the degree of a polynomial, whether it's positive or negative infinity, but this is the way you can actually figure it out. Once again, for our purposes, if we really only care about whether it's finite or not, we would just really could stop at D and E because it's infinity, but we can figure out specifically which one it is. So I wanted to go ahead and just, like the other ones, show you how to do it. All right, the last one here looks a little intimidating because we have a sine and we have an exponential. We have the limit as x goes to infinity of sine of 2x plus 3 times e to the negative x. Well, because these are completely separate, we have nothing to factor out, we have no fraction, we have no largest power of x to divide by, we just want to go ahead and do the limit of each part. Meaning I want to do the limit as x goes to infinity of sine of 2x plus the limit as x goes to infinity of 3 times e to the negative x. Well, you actually know both of these from the chart above. For the sine, I told you just sine of x, but what does 2 do? When you multiply the x by 2 in there, it just halves the period. It makes the graph oscillate faster. This is still D and E. Right, the graph is still oscillating, it's just going to oscillate faster. Now, technically, when we have D and E, we can pretty much stop, but this is a true D and E. This isn't it might be infinity or negative infinity D and E. This is just, it does not exist. For this one, when x goes to infinity of e to the negative x, you might say, well, we don't know that one. We don't know it directly, but if we plug in infinity, we would get e to the negative infinity. What's the limit as the exponent goes to negative infinity? This one, it's worth scrolling back up to explain. For e to the x, the way I like to think about this chart is that as x goes to negative infinity, it's telling me if my exponent goes to negative infinity, I get 0. All right, since the exponent's going to negative infinity, I get 0. This would be 3 times 0, which is 0. Technically, we would already be done because anytime you have D and E, it doesn't matter what you're adding to it. It's just D and E. So I didn't really need to figure this out, but I wanted to explain it as well, why this we really know. But you could have also, as another option, if you don't like what I just did, you can make the exponent positive by bringing it to the bottom. So this 3e to the negative x is the same thing as 3 over e to the x. And then you know the limit as x goes to infinity of this is infinity, and you can solve it like that. All right. But one point I wanted to make with this problem is that a true D and E like this, there is no idea of infinity or negative infinity. It's a real, does not exist. The other thing I wanted to mention is that when you have D and E, it doesn't matter if you add, subtract, multiply, or divide, it's just D and E. D and E overpowers everything else. Now, there are some exceptions to that. If we did something like, I'm only mentioning this, it's not going to be required to know, but if you did something like sine of x over x, or sine of 2x over x as x goes to infinity, because sine is between -1 and 1, then you would have the squeeze theorem set up, and the limit as this goes to infinity would be 0, and this would be 0, making this also 0. But when you add or subtract to D and E, it's not going to change it. You can get it to change by multiplication or division, and this is one of those examples. But once again, that's really high level. What we're trying to get at in this course is just the basics. How do you do limits? What are you looking for? All right, so we just had a ton of examples. What I wanted to do is just one more where it doesn't actually ask to do any limits at all. We have to know to do limits. So this says, find all the vertical and horizontal asymptotes of this given function. And what I wanted to remind you is that there can be 0, 1, or 2 horizontal asymptotes, but there can be any number of vertical asymptotes. So let's see what we remember based on not only this section, but previous sections. How do we do the horizontal asymptote? Well, that comes from the limits at infinity. We can do the limit as x goes to negative infinity of 3 minus x to the 4th over x to the 4th minus x squared. Now we could do this one out, but this is one we can use the shortcut on because the highest powers of x are the same on the top and bottom. And it's a limit at infinity, which means it doesn't matter if it's positive or negative. We can just do the ratio thing. And here the ratio is -1 on the top, and on the bottom it's +1. So the coefficient there is 1, and this one's -1, and then this simplifies to -1. And if we do the limit as x goes to infinity, what you might be thinking is, aren't we going to do the same exact thing? And you're exactly correct. When you do the limit as x goes to infinity of this, you also get exactly the same thing. Because that's -1, that coefficient, and this one's +1, and it's still -1. So you do have a horizontal asymptote here of -1, y equals -1. And in general, because of the way rational functions work, you're only going to ever have up to one horizontal asymptote. So you don't have to do both for rational functions. So rational functions can only have one horizontal asymptote. In general, functions can have two, but rational functions can only have one, which means if you have a rational function and you want to find all the horizontal asymptotes, you can do the limit as x goes to -infinity or positive infinity, whichever one you want to do, but you only have to do one of them. All right, what about the vertical asymptotes? Remember, vertical asymptotes occur where the limit is going to be infinite. And where the limit might be infinite is when the denominator equals 0. The limit is infinite if our denominator is 0 and the numerator is not. So let's go ahead and just figure out what x values make the denominator 0. We have x to the 4th minus x squared equals 0. Start by factoring this out. You can factor out an x squared, and you get x squared minus 1 equals 0. And this is a difference of squares, so you can even factor this too. We have x squared times x minus 1 times x plus 1 equals 0. And you set all of these equal to 0. To solve it, x squared equals 0 means x equals 0. Or x to any power equals 0 means x is 0. We have the middle one is x equals 1 by adding 1 to each side, and the last one we have x is -1 by adding to each side. And now we just do the limit of each one. If we get infinity, then it's a vertical asymptote. We know if we don't get infinity, then it would be a hole, but we're only interested in vertical asymptotes here. We got the limit as x goes to 0 of 3 minus x to the 4th over x to the 4th minus x squared. We know from past experience when we do a finite limit, a limit that's at not infinity or -infinity like this, we just plug it in first. That's our first goal. When we plug it in, we know the denominator is going to be 0 because that's how we figured out to use 0. When we plug 0 into the top, you just get 3. And this is, don't really care if it's positive or -infinity, but that means it is a vertical asymptote. And now let's do the same thing for 1 and -1. Notice that I didn't factor at all or try to factor. So let's go ahead and plug in limit as x goes to 1, 3 minus x to the 4th over x to the 4th minus x squared. Well, if you plug in 1, we should get 0 on the bottom because that's how we came up with it. And then when we plug in 1 on the top, we get 3 minus 1, which is 2. That's another one that's a non-zero over 0, which means it's positive or -infinity. So we have a vertical asymptote at x equals 1 as well. And then finally, what about -1? Oops. We're going to have the limit as x goes to -1 of 3 minus x to the 4th over x to the 4th minus x squared. And when we plug in -1, the denominator will be 0. The numerator will be 3 minus, and the -1 to the 4th is just 1. And that's 2 over 0 again, which means we have another vertical asymptote. So this one actually has 3 vertical asymptotes, one at 1, -1, and 0. Means it doesn't have any holes as well because that's all the discontinuities. And a horizontal asymptote of y equals -1. All right, so I know this is a pretty long section, but limits at infinity, they're very intricate, and kind of thinking about what we've done, we didn't even touch on a lot of different kinds of functions. Logarithms were one of them, some of the inverse trig functions, and there's a lot of other functions that we just can't deal with limits at infinity yet. So this is what is expected of you to know at this point.